looks good. All right.
All right. Okay, let's get started again. All right, so the last talk of the morning session and the last talk of the day, because remember we have a free afternoon today, will be Sven Bachmann. And today's talk will be about U1 and time reversal invariant SPT phases.
Thank you very much. So it is a continuation of what I've done before, but this is a specific work that is recently on the archive with Alex Bols, a postdoc at TTH, and Masa Ranama, who's my graduate student, and who should be there if it was not harder to get a visa into the US than a PhD. She's an Iranian citizen, and getting a visa in the US is apparently extremely hard. Anyway, so the setting is what I did, is the setting of yesterday. So the algebra is the algebra of canonical anti-commutation relations. So I have fermions. And U1 will refer to the presence of a charge operator. So at each site, you have a Qx, which is S star x Ax. So that the charge is just a number operator, okay? That you can check by the canonical anti-commutation relation is a projector, so its spectrum is 0, 1. Okay, so it in particular has integer spectrum. So in a subset lambda, so today it's important that I'm on the plane. So the lattice is Z2 and nothing else. So I have Q lambda is just the sum over x and lambda of Qx. All of these commute with each other. These Qx's commute with each other because they're even. And so because at each site I have integer spectrum, Q lambda has integer spectrum for finite lambdas. So let me write it like this, Q lambda finite. So spectrum of Q lambda is integer. In fact, is a natural number, right? It's positive here. OK, so that's a charge. So I talk about U1 symmetry. So you see, this is a good Hamiltonian if you want, right? This defines an interaction if you want to use the words that have been used. So you can look at the corresponding automorphism. I will denote the parameter neither s nor t, but phi. So this is this. You look at e to the I phi q lambda a e to the minus I phi q lambda. You take the limit as lambda grows to z2. That exists by everything we've seen so far. And that defines an automorphism or family of automorphism of the algebra. And what is special about it, rho at 2 pi, you see it already here, right? Because this has integer spectrum. E to the 2 pi I, an operator that has integer spectrum, is just the identity, okay? So this automorphism at 2 pi is the identity automorphism. Hence the name U1 symmetry, right? Because the parameter phi, you should think of it as living on the circle. Right. Good. So now that you have a charge, so let me just say a few words. Now that you have a charge, you can start talking about charge transport. So you can start talking about the Hall conductance, okay? And you remember in the non-interacting setting, we understood very well where quantization of the Hall conductance is coming from. You can ask the question now that I have a fully interacting setting, and you could prove that even in that setting, the Hall conductance is quantized. I will not go there, not because it's not interesting, because I want to talk about something slightly different. So in my title, I have U1. Now we know what that is. I can talk about charge and charge transport. I have another thing, which is time reversal. So just as above, a symmetry is given by an automorphism or a family of automorphisms. Time reversal here is also. So here it will be an anti-linear. I don't know if it's, if I shouldn't use the words automorphism because it's anti-linear, and an automorphism tends to be linear, but anyway, I will still use this, and that I will call tau on the algebra A. And really, it doesn't, so it has to be anti-linear. That's important. And the other property that I need is that tau square. So you remember, in a non-interacting setting for fermions, time reversal is an anti-unitary. So it's OK. It's the same thing as that. That squares to -1. OK? Now, if I have many fermions, you see one fermion is a good fermion. But if you have two fermions, it actually looks like a boson. And so in a sense, it depends a little bit where you are in your system. If you have a state with an even number of fermions, the time reversal should be bosonic, namely square to 1. And if you have a state which is an odd number of fermions, it should square to -1. And so that translates to saying that the automorphism is squares to theta, which was the parity operator. OK? So you remember I defined parity on the algebra, right? It's the automorphism that maps A to -A. And in particular, it maps an even number, an even monomial into itself and an odd monomial into minus itself. So that's why we pick here in an interacting setting, tau square has to be equal to parity. OK? Good. So now I will write, denote P. So let P be the class of pure symmetric stably SRE states. Symmetric here means they're invariant under both the U1 symmetry and the time reversal symmetry. So in fact, maybe I will actually write this. So that means omega is rho phi is omega, right? Now, you would like to write omega of tau is omega. Of course, you have to be a little bit careful, because if I were to write this, this is a linear map, while this, of course, together is an anti-linear map. So you take a bar here, and by this I mean that omega bar of A is omega of A star, which is also omega of A bar. OK, so that's a good notion of a state being invariant and an anti-linear morphism. OK, so I look at all of these states that are invariant under both symmetries and are stably SRE. OK, so somebody asked me, so stably SRE, again, from the point of view of what we've seen, for example, in Peter's talk, this is the trivial phase. There's no anyons, right? It's trivial. There's all the quasi-particle excitations are bosons. So that's a trivial phase. Nonetheless, because I impose symmetry, I am in what's called the symmetry-protected topological phase. Okay, hence the name, symmetry-protected. The symmetry is important. Good. Good. So here's a little theorem. So there is a map that I will call index 2 from P to Z2. So it's a map that takes a state, symmetric state, and gives you plus or minus 1, such that, so if you pick two states in there, so if omega 1 is, so maybe I will write the group G here. So G stands for U1 and Z2, where this is represents the time reversal. And so if I have two states that are G equivalent to each other, so I can interpolate from one to the other using a Hamiltonian or a TDI, which is invariant under this whole symmetry throughout, then index 2 of omega 1 is index 2 of omega 2. Now that is the crucial property, right? It says this map is an invariant of the SPT phases. Okay? Because if I take this one and I transform it, I deform it while staying in the same phase because I do not break the symmetry, then the index remains constant. Okay? So that, in a sense, that's what you really want to have in the first place. This map gives me an index of the phase. The other thing you want to say, but let me check whether this is this. Yes. So if you take two states, well, no, I don't want to write an if here, in fact, directly. The index of, so you take a state and you stack it with another one, right? Then, in fact, this is, again, this is a homomorphism if you want, so it's index 2 of omega 1 times index 2 of omega 2. Okay, so the index of a product is a product of the indices. And the last one, the last one is, of course, you could say, oh, this is beautiful, but your index just takes the value 1 all the time, right? It could be. Just like the Hall conductance could be 0 all the time. In fact, on this set, the Hall conductance is always 0. Okay? So you have to be careful when you do that to at least exhibit one example where the index take a non-trivial value. Okay? So, first thing, index 2. I told you omega 0 is always a product state, right? So so this index, this is what you want. This is in a sense the neutral element in here. So the index of that should also be the neutral element in the image. So for omega 0 product, which by the way, product, some people also call that factorize. It's the same. And so I will just write it this way. There exists an omega tilde such that index 2 of omega tilde is -1. So it's very explicit. So there is a non-interacting version of all of this. In that non-interacting version, precisely this Fou-Kane, maybe I should write this. This is the Fou-Kane Mealy. So there's two different papers where they construct explicitly, and this is old stuff, right? In a non-interacting setting, they construct states that have an index -1, and we show that our index is equal to their index. Okay, so that you can prove by going to a non-interacting setting, right? Because of course, all of this works for interacting states, but of course, it also contains non-interacting states, okay? So if you give me a Fermi projection, I can construct a state on the algebra which correspond to that Fermi projection. We'll not go into these details now, but that's it, okay? So that's, you may or may not be interested in that particular phase, but I think it illustrates a little bit what we want to do in this whole story, right? We have identified a notion of a phase, or an SPT phase, and we have constructed an invariant of these phases, okay? And an invariant means exactly what it is. In particular, it has to be stable within the phase, so under deformation, in this case, preserving the symmetry, okay? Now, I want to spend the rest of the time explaining how to do this, because it will use many of the ideas that we've seen in various lectures until now, and I think it's nice to see applications. Yes? So that's a good question. We don't know. In fact, it is believed to be a complete invariant, but we don't know. So for the rest of the talk, I'm going to explain how to construct this index. Okay? Good. So you see, the first thing I want to do is, so we talked about the quantum hole, and in quantum hole, you remember, I have this whatever plane, or I presented a disk last time with this phi of t. Okay, and it turns out the construction of the Z2 index will also use that picture, although it will not be related to any transport of anything. It's also important to emphasize it. But I want to do what I would also do for quantum hole, namely describe what I mean by inserting a flux here. And so I make a picture here. Caroline gave us also a picture. There were two disks and a line between the centers of the disks. And the flux was inserted in the middle. Her picture was this, right? And the flux was here, and there was a line. Right? You remember that, maybe? So, my picture is the infinite volume version of her picture. Okay? But they're equivalent pictures. In fact, you will see the construction is the same. But now I face my own, the problems that I created myself. I don't have a Hamiltonian. If you want to insert a flux, you have to have a Hamiltonian. So the first step is to construct a Hamiltonian. Okay? So my state omega bias, so I will do for SRE. It's stably SRE, so in principle I always have to possibly add a product state, but that's a technicality which is annoying, and I will not do it. So I'll do it for SRE. An SRE state, by definition, is what? Is one that I can obtain by an LGA from a product state. That's the assumption of being SRE. Okay? So now omega 0 being a product, you see, you can think of it as in a way like this. If maybe x1, on a tensor product of observables at single sites, that would just be given by, you pick your favorite, not phi, because I have another phi, so phi a x1 phi, phi a xn phi. This is a good product. I've picked a particular product, but all product states are equivalent. Okay? So you see, how would you, if you look at this state, you can think of that as being the ground state of a Hamiltonian. You just look at the rank 1 projection onto phi, right? 1 minus that is a good Hamiltonian that has phi in its ground state, right? So it has a good, what people sometimes call parent Hamiltonian, right? Which, okay, it's an interaction where at each site, if you want H0 site x is just the projection 1 minus phi, where this is a physicist notation for the spectral projection onto phi. Okay? It's an on-site interaction, right? But it totally fits everything we've seen so far. It's the simplest possible interaction you can think of. But because it's a product, it's easy, I can always do that, construct that sort of parent Hamiltonian. How do I get now a parent Hamiltonian for omega? Well, I pull it back by alpha, okay? So that, of course, I thought I was getting really weak at the end of the week, But so, you would have been impressed had I gone that. It's a little too thin here, Parent Hamiltonian of omega. Well, you just pull that back. So it's H. So I will just write H little x is alpha to the minus 1 of H0x. Okay? Now, this is strictly on site. Alpha, however, is an LGA. So alpha minus 1, by the way, is also an NGA. So Hx is a good almost local observable by the locality results that Bob explained. Okay? And here you already see I don't need to do the slice and no dice and slice. So, you know, by my definition of what is an almost local observable, of what is a TDI, this is automatically almost localized. So this defines a TDI, right? So this gives me, if you want, a Hamiltonian H, which is the parent Hamiltonian for the state omega. Now, this here, you know, if phi is invariant under the action, you know, omega 0 is invariant, so I pick phi here to be also a vector which is invariant under the action of the symmetry on site. But I have to be careful, right? Because alpha, I never said, in fact, in general, when I interpolate between this and this, I will have to break the symmetry in general. Okay? So I don't know whether these HXs are themselves, if this is an interaction which is itself invariant. So to make an invariant interaction, or let me use my own words, TDI, you just average over the group G. So typically you would say HX bar is, you know, if I just let me just average with respect to U1. So it's 1 over 2 pi, integral 0 to 2 pi, d phi, rho phi of h of x. That defines a new h bar of x, which is by definition invariant in the action of the group. And of course, you can do that sum of that with its time reversal inverse, and you get a perfectly invariant parent Hamiltonian. You could check that because this is gapped, this is again gapped. Use everything you've learned in the homework set and in the homework session, you would see that this is gapped again. All right, so now you see that allowed me now to not only think of omega as a state, but as the gapped ground state of that so-called parent Hamiltonian. Okay. Now I know how to insert a flux if you have a gapped ground state, and I will explain how to do that. Good. So now here's what I'm going to do. So maybe let me make a little picture. So here I have the plane, okay? And what I'm going to do is I can look at the upper half plane. We call it U, and I will. Oh, I've just erased what I wanted not to erase, but it's all right. I will define rho U phi, right? You see, rho, so that's the U1 symmetry, right? It's associated, it comes from an interaction or TDI or whatever, the QXs. So of course, I don't need, I can look at this only on the upper half plane, okay? So rho U is generated by, if you want, you know, let me just write it formally, QU, which is now, of course, you have to understand this properly, x in the upper half plane, QX. How do you understand that? Well, you take finite subsets of U, look at the corresponding automorphism, let this finite subset converge to the upper half plane instead of the whole system, and that gives you, again, a good automorphism. Standard construction. And once you have that, what you're going to do is you're going to twist this parent Hamiltonian by that half-plane automorphism. So now I have hx of phi. So let me not write the bar every single time. It's always the barred one. Is rho phi upper half plane of hx. So I twist my interaction terms in my TDI only in the upper half plane. Okay? Let us quickly think what I do. You see, these HXs are invariant under the action of the full group, okay, on the full row on the full plane. So if I was not to write a U here, I would have rho phi of HX is HX. Now, these HX are, however, local. So somehow, if I'm, so what can I say? I can say, if I'm far out on the lower half plane, right, the HX has only a little tail up here. So it will be essentially invariant under rho phi U, right? If I'm high up on the upper half plane, the hx, it almost doesn't see that I've cut in the lower half plane. So for this other reason, now I use the symmetry. In the upper half plane, these guys are also very close to hx. So really the difference, and you can make this explicitly using the sort of norms that Bob was using, and f functions and all that, hx of phi minus hx, is let me just write it like this, is small away from the horizontal axis. Okay? I mean, quite literally, the norm of this, the actual norm of each, for each fixed x, decays with an f function away from the vertical axis. Okay? That's a little exercise that you can do now at home because there's no exercise session anymore. All right. Good. So far, I haven't done anything. This is just it's a silly gauge transformation. I haven't done anything in my system. So now I've erased the picture. So let me continue this one. So now I'm in the plane, and I don't want to do that. What I want to do is just this line, OK? Remember what Caroline was doing. She said, well, I can do a gauge transformation in the disk. That gauge transformation influences the Hamiltonian only on the boundary of the disk. And then I can restrict it to just one part of the boundary. I want to do the same here. OK? But in order to do that, in a sense, I want to make this explicit. Now, Bob actually just told us how to do this. Right? So out of this, I have the family of states omega of phi, which are the ground states of the interaction h of phi. Oh, I have a family of gapped ground states depending on a parameter. I can construct the spectral flow. So spectral flow, or quasi-adiabatic evolution, or whichever name you want to use, it will tell you that I can obtain omega of phi from omega at 0, which doesn't carry an index, by an automorphism generated by a k. OK? K phi. That's what Bob just taught us this morning. OK? And k, you see, I can actually write explicitly what k is. I cannot thank Bob enough that he actually already wrote all of this. So it's this w. There's a gap. In fact, the gap is 1. So it would be the w function with 1. And then you write tau t at h of phi so let me use Bob's notation, h prime of phi dt. OK? And you see h prime of phi a little bit like this one. H prime of phi is something which is localized along the line. Hence, this one is a TDI. That is a TDI that is almost localized along, the axis x2 equals 0. This will be useful. And it's a TDI, so it's a sum of local terms. Now that I have that, I'm in business. You see, of course, these omega of phi's, because the Hamiltonian comes from a gauge transformation, the omega of phi also come from the same gauge transformation. I could also have written omega of phi is omega or evolved with the rho u, or its inverse in that case, right? I could have done that. But it's a mess because rho u is supported everywhere in the upper half plane. I don't want that. So that's why I need the spectral flow to first replace rho u by k, so q by k if you want. Okay, that should echo what Caroline was doing, right? You replace q by k, but k now you have an explicit control over it. It's, again, as Bob was saying, it's important. You have an explicit expression for this k. It's a sum of local terms, and you can explicitly see that these local terms away from the axis are negligible in norm. Okay, so now restrict or pick or drop the, no, instead of writing, we have a language called mathematics that allows us to do that. KLX, so I now have a KL, which I defined to be, this is a TDI, so it's a bunch of terms labeled by X, the sites, which arise from the X here, right? So KLX of phi is Kx of phi for x2 smaller than 0, x1, sorry, and it's equal to 0 otherwise. So I restrict this TDI, which lives in principle everywhere, but mostly along the line, but I restrict it only to the left-hand side. That is this picture. Okay? Again, that is exactly what Carolyn did in a finite setting. There's nothing. And that, for me, is the way to insert flux. Now, you define the flux inserted states as omega. So I am, of course, running out of symbols. So maybe I'll put a tilde here. Omega, or, no, let me, omega L of phi is omega of alpha KL phi. Okay? So these now are physically the states that correspond to the initial state upon which I've inserted a flux phi. Right. And you see, I use the SRE assumption here. I would not know how to do that if I just have a state in general. Here I really needed to go back to the product state, construct a parent Hamiltonian on the product state, and then go back to get a parent Hamiltonian on omega, which I can then twist. Right. Now, here's, I want to rephrase a little bit what we had here. So where do omega L phi and omega L, or omega L and omega 0 are the same, right? There's no twisting, there's no flux at all, differ. Well, let us just write a little equation for this. So let me make a box. So omega L phi minus omega of A. Right? I want to see how they differ for an observable A. So the best thing is I always have this possibility, well, maybe first it's omega of this is obtained from alpha k L phi. This I hadn't done anything, so it's the identity of A. Now omega, you see, if omega was highly correlated or highly entangled, even though this automorphism is nicely local, it could be that because of the high entanglement, in fact, this local transformation gets transferred very arbitrarily far out behind the moon. But it's not the case, because actually this is close to a product by assumption of SRE, again, short-range entanglement. So this is omega 0 of alpha of everything, of the same thing, right? And so I could say, well, it's omega 0. I move the alpha in, and I have alpha of alpha phi KL of alpha minus 1 minus, I would like to write this, but now I think I have, of alpha of A if you want. But alpha is an automorphism, so any A can be written as an alpha of A. So I could just as well have started with alpha minus 1 of A here. Would have been the same thing. So you see, now I don't have any problem, because this is really a product state. So it suffices to check the locality of this, right? So you see that indeed, this here, as we said, this automorphism is localized along the left half line. It's conjugated by alphas, but alphas are again local observable, local dynamics. And so the whole result will be, so when did I have until 20 past, right? Yes, you're there, yes, thank you. So, in fact, you could check the following little identity, which I will write because it's useful, and let you check. You just write the differential equation and you check that it's correct. So you see alpha of alpha phi KL of alpha minus 1. What is this? Well, it's the same as alpha phi of the twisted k. If you think of that as being a commutator, it will be obvious that this is alpha KL. Okay, so now KL being a sum of local terms, alpha of KL is a sum of local terms. Therefore, this is really an interaction, or a TDI, which is localized on the left half line. Okay, always up to tails, right? And when I say localized, it's always almost localized. So there's always tails, but I don't care about them. So it's a good. So these two states really differ only along the line. So conclusion: omega L phi and omega differ along, and I will give it the name L, where this here is L. Okay, good. So how do I want to continue? Right. Yes. In particular, I think it's important to say this. So in particular, that line extends all the way to infinity. So if I have an observable, arbitrarily far out, but along that line, that one will always see a non-trivial difference between these two states. Okay? So in particular, omega L of phi and omega are not unitarily equivalent. It's not equivalence in yesterday's sense. Now it's really really unitary equivalence. Because they differ at infinity, so to say, at infinity along L. Okay? So that criterion that Daniel gave us, that two states are unitarily equivalent if and only if they're equal at infinity, is just obviously violated. No? Along the line, they differ. Yes. Oh, absolutely. I mean, they differ. The K along the line is just a bona fide TDI. It has terms of order 1. The action is non-trivial. There's no reason for that to be trivial. Okay. So okay, that's a bit of trouble. But now you have to remember that this is not this is flux insertion. How did I get it? Well, I got it from rho. I restricted rho in a sense, right? But rho has something special. It's a U1 symmetry. So rho at phi and rho at phi plus 2 pi are the same. So maybe one thing you could do is to compare omega with omega at 2 pi. Because what happens, I know I move my hands a lot, but let's move my hands even more. If I am here, this is Sven, so I'm very tall. I'm out here very far out at infinity, right? What do I see? I see the action of this k, which is just like the action of q, right? Again, I will not really see that this action was truncated here, okay? So I, being naive here, even if I look very far, if I'm far enough, I will not see this is beyond my horizon. So for me out here, this evolution, this twisting that I see here could just be the twisting coming from the charge q. And so in particular, after I twist by 2 pi, I will see that I come back to myself, okay? That's of course true out here at infinity. It's certainly completely wrong if I'm sitting at the flux insertion point, right? But out here at infinity is what should happen. And that's indeed what happens. But that means that these two states that differ by a flux 2 pi are actually equivalent at infinity. They're kind of obviously equivalent at infinity everywhere around, not along the line. But if you look at phi that differ by 2 pi's, then they should be. So you would like to compare omega L at pi with omega L at minus pi, okay, where I will not learn that until the end. I have 10 minutes, so this is too late, right? So because, and really, you know, the only thing I will just say here is out here, you know, out here, omega of alpha KL at 2 pi is essentially the same as omega of rho upper half plane 2 pi, which is omega. Okay? So twisting by 2 pi far out at infinity is doing nothing. Hence, these two states will be unitarily equivalent. Okay? Yes? Oh, absolutely. And in fact, you see, in a sense, I have been using it here, but wherever, yeah. So it's important because when I say this here, saying these two states are the same except across the line, that's obviously true for observables that are strictly localized somewhere. But you could have a Wilson loop, and in order to get rid of them, you have to use the SRE assumption to show that really that what I said before was really true. So map it to the product state, in which case Wilson loops are trivially non-existent. But yes, so absolutely it comes in here. So these two states are unitarily equivalent. Okay, so so I could write omega L of pi. So I hope this is the one I want to write. Yes, is omega L of minus pi conjugated by the adjoint action of a unitary. Now, by Daniel's favorite theorem, namely Caddison's transitivity, that U, you can actually pick this U to belong to the algebra. Okay? It plays a role, but now, you see, now I'm actually getting there. 10 minutes, my goodness. I will have time to finish. All right. Erase the rest later. Good. Now here's a little proposition. I mean, I don't write everything. You know, what I just said is really the technical heart. I wave my hands, but it's a bit of work to actually prove everything, okay? But here's a consequence of that. Tau, let's go back to time reversal, has to play a role. Somehow, so far it hasn't played a role. Tau is unitarily implementable. In GNS of whichever of the two you take, because they're equivalent, so they have the same GNS representation. So let's take this one. Little sketch of proof, because it's nice. It's nice and it uses everything we've seen. So omega, now I'll just write this thing as just omega plus and omega minus to simplify my life. So omega plus is omega minus of add U. Okay? In fact, well, I don't want to use this one first. Wait, I could, but by something I didn't quite show, but I picked the charge. The charge is invariant on the time reversal. Okay? So tau of qx is qx. So e to the I phi qx under the action of tau becomes e to the minus I phi qx. This corresponds to plus phi, this corresponds to minus phi. So these two things are related by time reversal. Any physicist will tell you that. The flux time reversal changes the sign of fluxes or magnetic fields. Okay, but precisely now I write this is omega minus of, right? Omega plus and omega minus are related by this. So I think with my definition I have to put a U star, because I wrote that omega plus was omega minus conjugated by U of tau. Why is this good? Because now I have an equation where omega plus is equal to omega plus times an automorphism. All right? And in fact, you see, I'm sorry, there should be bars everywhere here because this is the tau has a, so this is wrong in my notes as well. Anyway, so now I have a state which is invariant under an automorphism. What do I know about those states? Uniqueness of the GNS representation implies add u star of tau is unitarily implementable. In GNS of omega plus. Okay? But because this is implementable by pi of u plus, this is implementable. Okay? So I have, so that gives me a t. So that gives me a t. So there's a unitary implementer. So we have that tau of pi of a is u star pi of a u, and in fact I tend, but it's not the same u, so let me not use the same letter. No, t star. Now that is a unitary, and it turns out to be an anti-unitary, okay? Okay, now I am slowly running out of time, so also of energy maybe. Here's a little, now here's a little lemma, which again requires a little bit of work. You can look at how, so if omega plus, so the GNS here is this pi, I don't know in which order I should write, h omega plus, okay? So you see, t omega plus has to be proportional to omega minus, okay? And here's what you can do. Well, you know, so this is necessarily the case because t maps the state little omega plus to the state little omega minus, so that has to be true up to a constant. And it turns out that you can pick things such that t square omega plus is, so maybe, yeah, so if I take this here, is c t square, let me just be, yes, exactly, is c omega plus. Okay? So, you know, in this whole thing, there's many phases that you can pick, but not all of them. Okay? It turns out one is independent of any choices. It's this one. T square implements parity because tau square is parity. So what does that tell you? It tells you, so, and of course, C, now that's just because of general properties, is either +1 or -1. So these states, and by the way, this would also be true for omega minus. So the statement is, once you go to the GNS representation, you have this state, omega plus and omega minus. They are eigenstates of parity for the same eigenvalue. Okay? And so the index 2 of the state is that value. So it's the parity of the GNS state. Okay? Plus or minus, they have the same parity, but it's exactly that parity. That's the definition of the index. Okay? Turns out, you see, that's why I needed all of these GNS abstract nonsense to actually construct this. But you can still say, well, but you know, I mean, do you really need the GNS representation? Because in particular, if you want to deform things, you jump out of GNS and it's a mess. So how would you show that this is, for example, constant in the phase? Well, it turns out, a posteriori, that this index, you have what I would like to refer to as a trace formula. You can actually express it in purely algebraic terms. That's a little calculation which is not particularly difficult to write, but that's what it is, where this is the state omega minus. So you take your state, you insert flux, minus pi flux, and you take this expectation value. You know, this is a little bit, you know, maybe you've seen that sort of expression, u star, t star. It's a little bit that sort of expression. It's an expectation value of, in a sense, you're going back in, from minus pi to pi in different ways, using u and using tau, and you compare these things, and the way the state behaves under that is exactly that index. Now that you see this, it's purely algebraic. You can believe there's some sort of you need some sort of continuous version of Cadison, but if you deform that state, you will deform everything in a continuous fashion. In this being a discrete value, everything will be constant under deformation. So everything will be constant within the phase. Okay? Again, that's a little bit of work, which I will not do here. I've just given you the construction. It fits, actually, if you look at what we get, this parity thing, this is exactly what the non-interacting index does. So it's clearly a generalization of the non-interacting index, and it's a perfectly well-defined of the U1 time reversal invariant SPT phase. And I will stop here.
Questions?
Sorry.
Did you make any assumptions on the time reversal automorphism? For example, like it seems that you didn't make any assumptions about locality. Crazy things.
Yes, good question. It acts locally. It acts strictly locally.
On site.
Yeah, it's on site.
Okay.
Yes, probably that could be relaxed to some sort of, again, TDI version, but yeah.
Thanks.
Up there.
In your first lecture, you related the index to a Fredholm index.
Yes.
And so can this index be written as the index of a Clifford linear Fredholm operator, which is like K-theory in degree 1?
So if you wanted that, so in a non-interacting picture, what will happen is you look at the spectrum of the Hamiltonian as a function of phi. And by symmetry, it will be symmetric. By time reversal symmetry, it will be symmetric. And in general, here's what you're going to get. You're going to get some, let me try to make it slightly symmetric, right? So you have some continuous spectrum, and as you insert flux, you will have some states localized around the flux insertion point, which will do, I don't know, that sort of bands. And of course, the same bands will be here. And this cannot be because here, because of time reversal invariance, you have to have degeneracy. It's called Cramer's degeneracy. So that's the sort of picture you will have. And the index will correspond to, so you pick, I don't know, you pick a value here, which is the Fermi projection, the Fermi level I talked about last time. And well, this is really a terrible choice, actually. Let me not take this one. There's some colored chalk, so let me take colored chalk. I will go, no, it's a good choice. And I look on between here and there, okay? And I count the number of eigenvalues of these branches that cross that particular line with sign. So here, this would be -1, okay? And you look that, in fact, if you move up and down, this -1 will stay. You see, if I was to go here, I have +1, -1. So the parity of it will stay. It's +1, -1, +1. Okay, so the parity of that number will stay. So it's +1. It will not become 0 anywhere. And so that index, our index 2 of omega, will be that number. So it's the number of crossings mod 2. Well, that's called the spectral flow. And that spectral flow mod 2 is related to a K-theoretic object. The spectral flow itself is, and the mod 2 version is also, look at, there's a paper of Denitis and Schultz-Baldes, Schultz, probably like this, Schultz-Baldes, that look into this very, very concretely, in particular with the K-theory point of view in the minds. But of course, that picture is a purely non-interacting picture. None of this remains if you go to an interacting setting.
So in the non-interacting picture, you also have like these gap-closing boundary modes that emerge. Can you say something about how this generalizes to the interacting picture?
Well, you see, in a sense, what is happening is when, so I'm on my plane, right? So here, I'm always in the bulk in a sense, but that flux insertion point plays the role of the edge. And really what we're doing, and you see that in this picture, is so when you insert a flux, you will create some excitations around the flux insertion point, which correspond to these edge modes. And the index corresponds to the parity of what people sometimes call the fluxon. So these excitations that are associated to the perturbation done by that, okay? So yes, there's an analogy, but it's not exactly the same, yeah.
I can answer that question in a physicist's language. So what condensed matter physicists would usually say is that if you insert a pi flux, there's a Kramer's doublet bound to the pi flux in this kind of topological phase. And I think this index is capturing that.
Exactly. So in the non-trivial phase, you have a Kramer's doublet. So it's more than one in a sense. It's two here. And if you have a trivial one, there's no Kramer's degeneracy. That's exactly what it is. Mm-hmm.
More questions? Yep.
So from your bottom expression following turns out, can we?
So this one?
Yes. Could you elaborate on the difference between the case with t squared equals to +1 and t squared equal to -1?
So I'm not exactly sure, but you see so the case t squared is -1. So I should write it like this. T squared omega plus minus is minus omega plus minus. Right? That's a non-trivial case. And that's precisely, I mean, I'm just going to elaborate this word on this word Kramer's doublet, because now you have two states, and you can look at the inner product. And so you see, what is it? So I can say that this is minus. I insert a t square here, and t omega minus. Now, t is anti-unitary, so this is equal to minus omega minus t omega minus. Okay? And this happens to be minus omega minus omega plus. Now, if you look what I've written, right, that implies that omega minus is perpendicular to omega plus. So when the index is non-trivial, you have really two states which happen to be time reversal images of each other, and they're orthogonal to each other. Okay? In the spectral flow picture, let me redraw a simple one. It really corresponds to doing this. So you see here, here you have a degeneracy, and you think of pumping this system from here to there. So here there's two states, so to say. So, and my Fermi energy is there. So it is filled. I slowly pump it up. Here, one half of the system will be filled. The other one will be empty. If you go to the opposite thing, what will happen, right? What did I want to say? No, what did I want to say? This is not what I wanted to say. This is not what I wanted to say. No, well, I don't know what's wrong with my picture, but that's not, so let me stop. I'm confusing myself. One, I should have the. I'm lost. So yeah, so let's stick with this. You get two states that are orthogonal to each other and time reversal inverse of each other, which corresponds to exactly what you see here if you insert plus flux or minus pi flux. Okay?
Got it. Thank you.
Just one more clarification question.
Yeah.
So where have we used that tau square? That tau square is the Fermion parity?
Well, yeah. I mean, we have used it where it's hidden, but really, when you want to show this, you have to relate it to the fact that you have to prove that these states are parity invariant and that t-square implements parity. Tau square is theta. T implements tau. So t-square implements parity. But again, there's all sorts of phases that you need to be careful of. But you use this in this line, in fact, quite heavily. But it's a good point. At the end of the day, it hasn't shown up really in what I had time to explain.
Thanks.
Any more questions? All right. If not, let's thank Sven again.
And I'd like to thank again the organizers, because it's really a good week. It's exciting. There's lots of good discussions. So I'm enjoying it very much.
And yeah, so that concludes today's program. So now it's time for lunch, and then whatever you'd like to do during the afternoon. And we'll see you back here at 9 tomorrow.